Okay, so what we're looking at here is a sample distribution for a proportion. Okay, so let's say that in our population up here, let's say that 50% of people like Powerade and 50% of people like Gatorade. Okay, so this represents the 1 represents the Powerade people, and the 0 represents the people who don't like Powerade. They like Gatorade better. So, okay, they either like Powerade or they don't like Powerade. Okay, so we're going to take a sample. This n equals 10. We're going to take a sample of 10 people, and we're going to take 1 sample. Okay, so what we got in here is that the out of the 10 people, 6 of them don't like Powerade, and 4 of them do like Powerade. Okay, so what this shows right here is that we've taken 1 sample. This bar goes up to 1, and that the number of people that like Powerade is 4. And then what this down here shows is the exact same thing, except it's a proportion. So we've done 1 sample, and the proportion of people that like Powerade is 0.4. Okay, now again, this is the sample. Okay, the population's up here, but we've done a sample from the population. Well, let's do another sample. Okay, well, it came out to be 0.4 again. So you see that the 4 doubled here and the 0.4 doubled here. And we're going to continue doing samples. Now that one came out to 30%. So 3 people like Powerade, or 30% on the 3rd sample. And then we're going to do a 4th sample. And that one came out to 4, so this bar went up to 3, and this bar went up to 3. So, and I'm going to do a few more. We got 3 again and 0.3. Okay, that one's 60%. So in our sample there, 60% of the people liked Powerade, and we got 6 of the 10, and then 60% right there. And there's 7. So that one came out to be 5 and 5. Okay. And then we're going to do another 5 came up, and another 4 came up, and that time 7 people. Okay, 7 people like Powerade, or 70% of our sample like Powerade. Okay, so what happens is if we were to keep doing samples, now I'm gonna do 100 samples. Okay, just to make this go quick. Okay, so we're going to do 100 samples. Look what happened. Okay, we got a distribution that's roughly unimodal and symmetric. Okay, so what do these 2 sampling distributions show? Well, this distribution here shows the number of people that liked Powerade in our sample of 10 people. So most of the time we got 5. But we got a lot of 4s, and then we got a lot of 6s, and then we got beyond that 3s, and these are 7s, and then beyond that these would be 2s and 1s, and we got no 0s, and then these would be 8s and 9s. Okay, and this down here looks like the exact same graph as this, but this is in proportion. So this is 50%. So the bar that's the highest is the 50% bar, and then the 40% bar is here, and the 30%, 20%, 10%, and then this would be 60, 70, 80, and 90. Okay, and then we're going to add some more samples. So let's just do well, we have 110 here, so I'm going to just kick this up, keep doing it, and let's go up to about 1,000. Okay, so we did 1,010. So what happens is that look what happened to our distribution. Okay, if we did 1,000 samples of 10 people, asking them, you know, do you like Powerade, and knowing that the population is 50% like it, then this is what our distribution would look like for the number of people who said yes, and this is what our distribution would look like for the proportion of people who said yes. Okay? Alright, so let's change this a little bit. And now we're going to go and I'm going to change our p-value to 0.2. So these here are the people who don't like house, and these here are the people who do like house. So 20% of people like house, 80% of people don't like it. Okay, so we're going to do a sample of 10 people, and look what came out. Okay, in our sample, 30% of people said they liked house. So it plotted a 3 here and a 30% there. And then we're going to keep on doing samples. That came out to 40%, 10%, 10% again, and then 30%. Okay. So we keep plotting these samples of 10 people. Okay. Well, let's just kick it up. We're going to do 1,000 samples. Let's just do 1,000 samples all at once. Okay. So what happened? Well, this is the issue that we ran into in the last chapter. This is why we had the success failure condition, because this is going to be roughly unimodal and symmetric, or looks like it could be normally distributed, except that the tail gets cut off on this side. Well, the reason is you can't have less than 0 people who don't like house. So the problem is our success failure condition is violated. Okay, so that's why this is happening here. Okay. So what can we do? Well, we could take larger samples. So let's instead let's take samples of 50. Now, knowing that 20% of people like house, 20% of 50 is 10, and then 80% of 50 is 40, so the success failure condition is met. So let's just do 1,000 samples of 50 people, and look at that. Okay. Now we have a distribution that's unimodal and symmetric, and the tail's not cut off. Okay. So what this shows here is this again is the number of people who like house. So where is this centered at? Well, this is going to be centered. What's the largest bar here? Well, the mean is 9.946, which is an approximation of if we took a sample of 50 people and 20% of people like house, we would expect this to be centered at 10, because 20% of 50 is 10. Well, this down here looks exactly the same, doesn't it? Okay, except that it's not the number of people who like house, it's the proportion of people that like house. Well, where would we expect this to be centered at? Well, we know from the population that 20% of the people like house. So we would expect in our sampling distribution that this would be centered around 0.2, and it is. It's centered at 0.1989. Now, understand that when you take a sample, variation is going to happen. Okay, so not every sample is going to come out to be 0.2. Okay, you look down here, some of these are pretty close to 0. And then you look up here, it looks like these could be close to like 30%. Okay, so our samples are good approximations of what our population looks like, but we expect variation from sample to sample. Okay, so that's something to keep in mind in terms of sampling distributions. Okay, so this is what you looked at last chapter. This is, what would this be? Well, this would have a mean of NP and a standard deviation of the square root of NPQ. That's where that's coming from. Okay, this has a mean of approximately what P is, not NP, but P. And we have a different standard deviation, although the variation in this looks exactly the same as this, but the standard deviation is not the same, because we're not dealing with the number of successes here, we're dealing with the proportion of successes here. So what we're going to look at in this chapter is that in order to get this distribution down here, we really can derive it from this distribution up here. And it's going to be very simple. All we're going to have to do to go from a center of NP to a center of P, all we got to do is divide by N. Okay? And then to get the standard deviation, if we divide the mean by N, we would divide the standard deviation by N. And that's going to be what we're going to wind up doing to get this new distribution down here, which is really not anything new. Okay, it's just derived from what we already know. Okay, the second thing I want you to notice is let's look at a distribution here. We got a sample size of 40. Now this sample looks like it's centered, I don't know, around 0.3, 0.4. Okay, and this is 200 samples. So you notice what that distribution looks like. Okay. So it goes from, I don't know, looks like maybe 10% to 55%. The lowest is 0.13 and the highest is 0.55. Okay. And we did 500 samples. Now what happens, we go from 40 to 120. We triple the sample. What happened? Well, you might say, well, it looks like it got squeezed in. It did. Okay. So what happened here is, I think that we went on our last distribution went from 0.313 to 0.55. This one here goes from 0.44 is the lowest, is the highest, and 0.2 is the lowest. Okay. So this over here, this isn't working right now. Come on. Okay, yeah, that 0.2 is going to show up highlighted. Oh, there it is. 0.22 is the lowest, and then if we go up here, one more. Let's see what gets highlighted. 0.44. So what happened when we took a larger sample? Well, what happened is the variation decreased. When you take a sample size of 40, you get a wider distribution. When you get a sample size of 120, you get a narrower distribution. And then with 160, you get an even narrower distribution than that. So what that means is that the larger the sample size we're going to take, the less variation. Okay? So we would kind of expect that intuitively if you think about it. If I was to sample, let's say that that the proportion of people that like Powerade was 50%, and I was to sample 10 people, I could get anywhere from probably 20 to 90%. Okay. However, if I was to sample 1,000 people, I probably wouldn't get from 200 to 900. I probably would get a much narrower distribution. Like I might get as low as, I don't know, 3 and change, and maybe as high as 7 and change. So you could see that going from 2 to 9 when you're centered at 5, you're going to have more variation than if you were to sample 1,000 people and you would only go from maybe 375 to like 725. Okay. Now that doesn't mean that it's a better sample. It just means you're going to have less variation. Notice that even though I sample at 40 or 80 or 120 or 160, they're all pretty much centered in the same spot. Okay, they're going to the mean is going to be a pretty good approximation of what that true proportion is. Okay, now you might say that, well, they're not all centered in exactly the same spot. Well, that's because you have variation from sample to sample. Okay, what a sample is going to give us is a good approximation of what that p-value is, but it may not hit right on it. So we're going to also take that into account in future chapters as we try to approximate what that p-value is. Alright, so now we're going to look at sampling distributions for proportions, and we have an example here. Suppose we sample 900 M&Ms, and we take the number of blue M&Ms, and the true proportion P is 10%. Okay, that's what that P means. So taking what we know from last unit, in order to use the binomial model, three things had to be true. The probability of getting a blue M&M has to be consistent. It does not change. Okay. So that would be the first condition. The second condition is there's only two things that can happen: success or failure. And either the M&M's blue or it's not. So that's success. If it's blue, it's not blue, it's failure. And then each trial is independent. So each time we take 900 M&Ms, each of those separate trials would be independent from the other. So there's no reason to think that one trial would affect another. So we talked about our model had a mean of NP and the standard deviation of the square root of NPQ. Yeah. And then the last thing we had to do, of course, is check the success failure condition, right? So NP had to be at least 10. So 900 times 10% is 90, and that's at least 10. And then failure would be 900 times 90%, and that would be 810. And that's at least 10. So we can use a normal model. So what would the mean be? Well, the mean would be NP, and that would simply be 900 times 0.10, which would be 90. And then the standard deviation would be the square root of 900 times 0.10 times 0.9, and that would be 9. So our normal model would have a mean of 90. Mean of 90. And then one standard deviation would be 99, and then 2 would be 108, and then 3 would be 117, and then down this way we would go 81, 72, 63. Okay. So what that means is that if we were to take multiple samples of 900 M&Ms, 68% of the time we would get between 81 and 99 blue M&Ms in our sample. We would not get 90 blue M&Ms in every single sample of 900 that we took. Okay, most of the time we would get 90, but there's going to be some variation in there. Okay, just because the population of M&Ms of all M&Ms, 10% of them are blue, doesn't mean that in every single sample that we take we're going to get 10% blue M&Ms. Okay, there's going to be variation in there. Okay, so 68% of the time we would get between 81 and 99 M&Ms, and then 95% of the time we would get between 72 and 108 blue M&Ms, and then 99.7% of the time we would get between 63 and 117 blue M&Ms. Okay. So we have this model, and the mean is going to be NP, right? And we're going to divide that by n, and we're going to get a mean of p, and I'm going to explain this in 1 minute. Okay, and then the standard deviation is the square root of NPQ, and we're going to divide that by n, right? Now, back in Algebra 2 you learned that a square root was a 1/2 power. So this is really NPQ to the 1/2 power divided by n, like that. Well, whenever you basically have 3 variables in this expression, all raised to the 1/2. So this is really n to the 1/2, p to the 1/2, q to the 1/2 divided by n to the first. And you have an n to to the 1/2 over an n to the first. So what do you have there? Well, you would subtract, right? You would bring this down and you would subtract this 1/2 from this 1. So 1 minus 1/2 is 1/2. So you get this, right? P to the 1/2, Q to the 1/2, N to the 1/2. Well, everything's at a 1/2 power, so we could do this whole thing. Okay. So what we just did is we just took our normal distribution for the number of occurrences in a binomial situation, and we converted it to the proportion of occurrences in a binomial situation. So in other words, what do we expect our proportion to be? What do we expect the mean to be? Well, if our proportion of blue M&Ms is 10%, then on average we expect that 10% of the time we expect 10% to be the mean of our new normal model. We expect 10% to come up the most. Okay? Now that doesn't mean in every sample that we do that's going to happen, but that's our expectation. And our new standard deviation will simply be the square root of PQ over N if we're doing it for proportions. Okay, not the number of occurrences, but the proportion of occurrences. So what do we get? We get a mean of P and a standard deviation of the square root of PQ over N. So in dealing with a distribution for proportions, we have a normal model centered at P with a standard deviation of the square root of PQ over N. Okay. However, when we are sampling, we will never have P. Okay, so let's say that we're doing a sample, and we're looking at the proportion of people who are going to vote for a candidate. Well, we will have we want to know if that person's the majority. They're over 50%. Well, we don't know that. We don't know if they are or if they're not. But there is some proportion out there of people that are going to vote for this candidate. Okay, we just don't know what it is. Okay. So what we will have is what we call P hat. So when we do a sample, we get the proportion of people that will vote for the candidate. Now this P hat is an approximation of P. We expect it to be pretty close, okay, if we do our sample right, though we do expect some variation. Okay. So for our sample distribution, we also have to use P hat instead of P, because P is unknowable in many situations. Okay. So our sample distribution for proportions will have a distribution that can be approximated by a normal model. But it being modeled by P hat, and the standard deviation will be square root of P hat Q hat over it. Okay? So since we are now sampling, there are conditions for our sample to be valid and reliable approximation of P, the true proportion from the population. First thing is our sample must be random or representative. Well, we talked about this back in chapter 13. Chapter 12. Chapter 12, yeah. Okay. Can't just do a convenience sample. Okay, you gotta randomization is a way to get a representative sample. Okay, or if we know that the sample is representative, sometimes we do samples that we know are representative of the population. So suppose you were to go down to a PE class. You were just to walk into the gym on some random period. Okay, and you were to say, oh, okay, you look around the gym and you say, there's a bunch of 9th graders, 10th graders, 11th graders, 12th graders. There's a mix in the gym of different socioeconomic groups. There's a mix of different racial groups. You say, oh, this looks like a pretty good snapshot of what the student body of Brian McMahon looks like. So you say, okay, well, I'm going to sample everybody in the gym. That's a representative sample. Now you may say, well, back from chapter 12, that's a cluster sample. In effect, it is. But the fact that you know that it's representative, sometimes you can say, okay, I'm going to use this sample because I know it's representative. Okay. The second thing is our success-failure condition. Okay. And that is that we said an NP and NQ must both be 10, but we don't know P and Q, right? So you got to use P hat and Q hat. Whenever you don't know P and Q, use P hat and Q hat. Okay, the next thing is our less than 10% condition. Remember that when you sample, we talked about this in the previous chapter about the fact that when you're sampling without replacement, in effect, every time you pull somebody out of the population or something out of the population, you change the proportion of successes that's left in the population. Okay, so as long as we sample less than 10% of the population, we don't significantly alter that proportion. Okay, so when we sample, we got to make sure we're sampling less than 10%. And then the last thing is each sample must be independent. Okay, so if you're doing a systematic sample and you say, you go down a Stop and Shop and you sample every 5th person coming out, and then you go to another Stop and Shop. Let's say that you saw somebody that you sample. Well, what you did in one sample cannot affect what you do in another sample. Okay, and most of the time, samples do not affect each other. So that's usually not an issue. Okay, so this is basically going to be our model for our sample distribution right here as we move forward dealing with proportions. Alright, so in example 3 here, we have of all the cars on I-95, 80% exceed the speed limit. So find the probability that the next 50 cars we see will, at least 45 of them will be speeding. So in this case, we do know what P is. That's this. That's all cars. So that's 0.8. And our P hat that we want is, we want to see 45 out of 50. So P hat's going to be 45 out of 50, which is 0.9. Let's put that over here. We want to see at least that many. And then we got to do the standard deviation. So the standard deviation is going to be, now, here's the deal when you have P and P hat. P is the stronger of the two, because P is the actual proportion. So when you have P, which you rarely will, you use P. Okay. So in this case, we do know what P is. Okay. So we're going to use P and not P hat. Okay. So we're going to do 0.8, 0.2, and N would be 50. Okay. So we'll do a little math there. Turn the calculator on, that'll help. Alright. Square root. So we're going to do 0.8 times 0.2 divided by 50, close parenthesis. and that's 0.0565 or 0.05657. Okay, so what are our conditions? Well, we'll assume that our sample is representative because we don't know it's random. So we'll assume that our sample is representative. Yeah. NP and NQ, so let's do 0.8 times 50 is 40, and that's at least 10. And then 0.2 times 50 equals 10, and that's at least 10. So success failure condition is met. Failure condition is met. And then the next one is 50 cars on I-95 is definitely less than 10%. And 10% of all cars. And then we would say that our sample is independent. Our sample of 50 cars should not be influenced by any other sample. Of 50 cars is independent. Okay. So now we just go and we do a normal model. Okay, so we're going to go to second distribution, norm CDF. So our lower bound is 90% to an upper bound of 100%. Our mean is 0.8, and our standard deviation was 0.05657. 0.05657. And it comes out to about 3.8%. Okay, so the probability that we will see 90% of the cars speeding in a 50 car sample is going to be 90%. So what would that look like? Well, our normal model will look like this. You could probably draw yours better than I drew mine. Our mean would be there. Our 0.9 would be here, and we would shade to the right, and this would be 0.0384. Again, remember this is an approximation. So our answer would be approximately 3.84% of all samples of 50 cars will have at least 45 speeding. Okay, so that's how we use a normal model to solve a proportion problem where we know P, and we also are trying to figure out using P hat what proportion of samples will have a certain condition.